Hello friends, continuing with the chapter of current electricity. Today we take up third part of the topic measurement of EMF, that is parallel grouping of cells. Previously we have studied about series grouping of cells. Now we take up parallel grouping of cells. Now we take up point by point. First point, need. When circuit requires low PD and high current for its operation, then cells are connected in parallel. I repeat, when circuit requires low PD and high current for its operation, then cells are connected in parallel. Now question rises, how cells are connected in parallel? Let us see. When positive terminal of each cell is connected to one point and negative terminal to the other point, the cells are said to be connected in parallel. I repeat, when positive terminal of each cell is connected to one point and negative to the other point, the cells are said to be connected in parallel, as shown in diagram. You can look into the diagram. You see the positive terminal of E1, E2, E3, En is connected to one point and negative terminal of E1, E2, E3, En is connected to the other point. It means the cells with EMF E1, E2, E3, En are connected in parallel. Okay. The third point, equivalent EMF and internal resistance of the parallel combination. Now here we are to find out equivalent EMF and internal resistance of the parallel combination of cells. So first we consider two cells in parallel and then we'll generalize the result for n cells in parallel. Now here consider two cells with EMFs E1 and E2 having internal resistance R1 and R2 respectively connected in parallel as shown in this diagram. Now current equation for the point G. Now consider point G in the circuit. Let I1 be the current supplied by the cell with EMF E1 and I2 be the current supplied by the cell with EMF E2 to the load resistance R. Let I be the total current drawn by external load R. Then using Kirchhoff's current law for the point G, we can write minus I plus I1 plus I2 equal to 0. Okay. So using sign conventions and Kirchhoff's current law for point G, we write minus I because I is moving out from point G. We write plus I1 because I1 is entering point G, and we write plus I2 because I2 is entering point G, and minus I for because I is leaving point G. I is equal to I1 plus I2. Let us mark it as equation 1. Now potential difference across CD can be expressed as VCD is equal to E1 minus I1 R1. Let us mark it as equation 2. And potential difference across EF can be expressed as VEF equal to E2 minus I2 R2. Let us mark it as equation 3. Equation 2 and equation 3 has been written as per EMF equation of the cell. Now since cells are connected across the same point G and H, therefore PD across EF must be equal to PD across CD. Therefore VCD must be equal to VEF, or let it be equal to V. Now since VCD is equal to VEF equal to V, say, therefore equation 2 and equation 3 can be written as V is equal to E1 minus I1 R1. Here VCD has been replaced by V, and V equal to E2 minus I2 R2. Here VEF has been replaced by V. So this is equation 2, this is equation 3. Now we have removed the suffixes. Now from equation 2 we have I1 equal to E1 minus V divided by R1. Let us mark it as equation 4. And from equation 3 we have I2 is equal to E2 minus V by R2. Let us mark it as equation 5. Now substituting the values of I1 and I2 from equation 4 and 5 in equation 1, we get I is equal to E1 minus V by R1 plus E2 minus V by R2, or it is equal to E1 by R1 minus V by R1 plus E2 by R2 minus V by R2, or we can write it as equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. Now taking the term V into 1 by R1 plus 1 by R2 towards left hand side and I towards right hand side, we have V into 1 by R1 plus 1 by R2 is equal to E1 by R1 plus E2 by R2 minus I. So we have taken I to the right hand side and we have taken V into 1 by R1 plus 1 by R2 to the left hand side, and thus we have rearranged the expression. Now from here we take LCM of the left hand side and then write left hand side as V into R2 plus R1 divided by R1 into R2, and right hand side equal to E1 by R1 plus E2 by R2 minus I. Okay. Or V is equal to E1 by R1 plus E2 by R2 into R2 into R1 divided by R1 plus R2 minus I into R2 into R1 divided by R1 plus R2. Now the term R2 into R1 divided by R1 plus R2 has been shifted from left hand side towards the right hand side. So on further simplification we get V equal to E1 R2 divided by R1 plus R2 plus E2 into R1 divided by R1 plus R2 minus I into R2 into R1 divided by R1 plus R2, and V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R2 into R1 divided by R1 plus R2, or we can write it as V is equal to E equivalent minus I into R equivalent. Let us mark it as equation 6, where E equivalent is E1 R2 plus E2 R1 divided by R1 plus R2, and R equivalent is equal to R2 into R1 divided by R1 plus R2, or we can write E equivalent by R equivalent. When we divide E equivalent by R equivalent, we get E equivalent by R equivalent equal to E1 by R1 plus E2 by R2, and 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Now this is how we have expression for equivalent EMF of two cells when connected in parallel, and also the expression for equivalent internal resistance of the combination of two cells in parallel. Okay. Now fourth, equivalent EMF and internal resistance when M cells are connected in parallel. Thus, when M cells of EMFs E1, E2, E3, EM having internal resistance R1, R2, R3 and Rm are connected in parallel as shown, then E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2 plus E3 by R3 plus so on plus Em by Rm. So we have followed the expression of equivalent EMF and equivalent internal resistance of parallel combination of two cells. So following that expression, we can write for M cells the expression as E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2 plus E3 by R3 so on plus Em by Rm. And for internal resistance, we have the expression as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on plus 1 by Rm. So we have generalized the result for M cells in parallel. So here are the expressions. This is expression for ratio of EMF to internal resistance, and here is the relation for the equivalent internal resistance of the combination. Okay. Fifth, equivalent circuit. Here we have drawn the equivalent circuit of the combination of M cells in parallel. So this cell has equivalent EMF EEQ and equivalent internal resistance REQ and external load R. Now sixth, current through the circuit or load resistance R. Let I be the current that flows through load resistance R, then I will be equal to E equivalent divided by capital R plus R equivalent. So this is the expression for the current through the load. Now discussion, point by point we take up discussion. Number 1, when EMF and internal resistance of each cell is same, that is E1 equal to E2 equal to E3 equal to En equal to E say, and R1 is equal to R2 is equal to R3 is equal to so on Rm equal to R say, then E equivalent will be equal to E and R equivalent will be equal to R by M. Now current through load R is I equal to E divided by R plus R by M. Just substitute the value of E equivalent as E and R equivalent as R by M in the above expression. So we get I is equal to E divided by R plus R by M. 2. When MR is equal to R and power dissipation is maximum, then I is equal to E by 2R is equal to ME by 2R. 3. When capital R is very large as compared to R by M, then R by M is neglected and current becomes I is equal to E divided by capital R. 4th, when R is very small as compared to R by M, then capital R can be neglected and current becomes I equal to ME by small r. Okay. So this is how we deal with the expression of current through load. Now assignment 3.7 continued. Question number 8. Two cells of EMFs E1 and E2 have internal resistance R1 and R2 respectively. Deduce an expression for the equivalent EMF of their parallel combination. Question number 9. A part. Describe the formula for the equivalent EMF and internal resistance for the parallel combination of two cells with EMFs E1 and E2 and internal resistance R1 and R2 respectively. What is corresponding formula for the series combination? B part. Two cells of EMF 1 volt and 2 volt, internal resistance 2 ohm and 1 ohm respectively are connected, number 1 in series, number 2 in parallel. What would be the external resistance in the circuit so that the current through the resistance be the same in the two cases? So here is the answer for it. Assignment 3.7 continued. Question number 10. Two identical cells of EMFs 1.5 volt each joined in parallel provide supply for an external circuit consisting of two resistances 17 ohm each joined in parallel. A very high resistance voltmeter reads the terminal voltage of the cell to be 1.4 volt. Calculate internal resistance of each cell. And here is the answer for it. So you solve these numerical problems on the basis of the text that you have learnt. Thank you so much. Next time we'll take up part 4 of measurement of EMF. Till then, goodbye.